Hello, everyone. So for the last couple of hours, we have talked about CPM. And today, I'm going to introduce PERT and how it could be implemented to the real world. Okay, so let me share my screen. Okay. Okay, so both CPM and PERT, the analytical methodology for predicting the cost and the completion time of the project. And the PERT is usually concerned just with the time taken. But the CPM looks at the trade-offs between the cost and time. So if you recall, last time we talked about the process of the crashing a project using the linear programming, right? So that's the procedure for investigating time and cost, time cost trade-offs. So today we are going to talk about PERT just briefly. And I got to tell you that the PERT is better suited when there is a much uncertainty and when the time pressures were very high and the cost would be the secondary issue, right? And I'm going to talk about in a little bit, but the PERT handles this uncertainty issue of the time required to complete an activity by developing the three estimates and then computing the expected time using the beta distribution, okay? Okay, so one of the shortcomings of the CPM is the assumption that the duration of each activity is deterministic. But you know, for many projects in reality, this is clearly not applicable, right? So PERT is an attempt to correct these shortcomings of CPM by modeling the duration of each activity as a random variable with known mean and standard deviation values, and then derive a probability distribution for the project completion time. And for each activity, PERT requires the user estimate these three different quantities. So usually A stands for the estimate of the activity's duration under the most favorable conditions. And B stands for the estimate of the activity's duration under the least favorable conditions. And M stands for the estimate of the activity's duration under the normal condition. That's going to be the most likely value for the activity's duration, okay? And one of the most important assumptions of PERT is that the duration of an activity is a random variable with beta distribution. So if the activity's duration follows a beta distribution, then it can be shown that the mean and variance of the activity's duration may be approximated by these two formulas. Okay? These two formulas. So the beta distribution is unimodal with finite endpoints like this, A and B. And it can be skewed either to the right or left. Okay. So here, the prefix uni means one, right? You know, and the mode is the most frequent value. So the unimodal distribution is a single peaked distribution, just like this. Okay. So that's the most frequent value in here. Okay. And the PERT requires the assumptions that the duration of all the activities are independent. Then for any path in the project network, the mean and variance of the time required to complete the activities on the path are given by these two different expressions. Then if you let CP is the random variable denoting the total duration of the activities on a critical path found by CPM, then PERT assumes that the critical path found by CPM contains enough activities to allow us to invoke the central limit theorem and conclude that the total duration of the activities on a critical path is normally distributed. So in other words, the central limit theorem can be applied so that the sum of the durations of the activities on the critical path has approximately follows a normal distribution. Okay. So with these assumptions, we could answer the questions concerning the probability that the project will be completed by a given deadline, given date. Okay. Okay, then let's consider this activity on arc network diagram. Okay, and suppose the optimistic estimate and pessimistic estimate and the estimate of the most likely values for the activities durations are given in this table, right? Those are the A, M, and B, right? A, B, and M for each activities in this AOA network diagram. And we'd like to determine the probability that the project is completed within 42 days, okay? Okay, then first using this formula, we can obtain the mean and the duration, mean and the variance of the duration of each activities like this, right? Of course, the fact that arc 5-6 is a dummy arc, which yields the mean and variance values of the duration of this activity is going to be equal to 0, okay? And next step is to find the critical path by using the value mu as the duration of each activities, okay? Then the critical path would be BEGR okay, or 1, 3, 4, 9, 10 in this network diagram. And the critical activities includes B, E, G, and R. So once you identify the critical path using the CPM, then the next step is to find the mean and standard deviation of the sum of the durations on the critical path. Okay. So again, the CP is the total duration of the activities on a critical path. So the expected completion time of the project is going to be 39.7 days. And the variance for the CP going to be 7.61. And then the standard deviation for CP is going to be square root of 7.61. Right? So standard deviation for CP is going to be 7.61. That's going to be 2.759. Okay. So, okay. So in that case, we can say that the completion time for the project follows normal distribution with mean value of 39.7, right? And the standard deviation of 2.759. Now we want to find the probability that the project will be completed within 42 days. So that's going to be the probability that CP is less than equal to 42, right? So in this case, the standardizing and also applying the assumptions of the CP is normally distributed. So what I mean is, I don't have this. Okay, I thought I have the another screen. But obviously, I don't have that. So I'm talking about probability CP is less than equals 42. That's going to be same as probability CP minus the mean value 39.7 divided by the standard deviation 2.759, right? It's less than equal to 42 minus 39.7 from here divided by 2.759, right? So if I substitute this value with X, then, X is a standardized normal random variable, right? With mean value 0 and standard deviation of 1. Is that correct? So this can be rewritten as probability X is less than equals this value is going to be 8.336 from my previous computation. So That's going to be same as probability x is less than equals 8.336. Okay. So here, using the standard normal table, we can find the values. I believe in Excel. Okay, right here. In Excel, you can use the function norm dot s dot distribution dist. Inside parentheses, you can put this value 8.336. Then put after comma true, and then close parentheses. So if you provide true here, that we're going to give you cumulative distribution function value, CDF. While if you put false over here, then it's going to give you the PDF, probability density function. Okay. Let me see. Let me recall. Okay. Oh, I see. Okay, so this screen just shows a sample of the standard normal distribution table. So to determine the area under the curve between 0 and 0.36, for example, you need to look in the intersection cell for the row leveled 0.3, right? And then column leveled 0.06, okay? And then the area under the curve is going to be 0.1406. So for example, here, if you have this value is 0.36, then this area under the curve will give you the value of this 0.1406. Okay. So of course, if you want to obtain the area under the curve between the negative infinite, right? So here you have all the way here. So here you have negative infinite. And this value 0.36. Then simply you just need to add 0.5 because let me change this color. Because this area is going to be equal to 0.5, right? So you just need to add 0.5 to this, which will give you 0.6406 something, okay? So this value will be same as probability x is less than equals 0.36. Okay. And how about our case? Okay, it's not. I think I made a mistake. Sorry, it's not the 8.336. Sorry, it's gotta be 0.8336. So it's gonna be 0.8336. Okay. Uh, okay. So I just briefly introduced how the PERT approach works. So now let's take a small example. So let me first give you like 5 to 10 minutes. Then why don't you pause this recording and then try to work it out by yourself. And then come back whenever you're ready. Okay, so please read through the problem description and then try to get the critical path using the CPM method. Then I believe this couple of questions can be easily answered. And then later on, especially these two questions, question number 6 and 7 for the PERT, and then we can work it out together, okay? Okay, so let's try to answer for this series of questions. So regarding the first one, is asking us compute the expected duration of each activity based on the 3 time estimates. So so for the first question, so what you need is okay, using this formula. We need to obtain the mean duration of each activity. So this time, let's just use this first formula, okay? So how much is that for this value? That's gonna be 1 plus 4 times 2 plus 9 divided by 6. So let me see. Okay, so let me get the Excel file. Okay, so I just copied this whole table to Excel. So let's work on the computation. For the mu, that's going to be A plus 4 times M, right, plus B, and then divided by 6. So that's going to be 3, right? So I'm going to just copy the formula, paste. Okay, so we've got the mean duration for each activities. Okay, so I'm gonna highlight it with red, and then later we are going to need the variance values, right? So let's do the computation. That's gonna be E minus A to the power 2 divided by 36, right? And now we're gonna copy the formula, paste that. And I'm gonna have different color, or let's use the same color. Okay, red, like this. Okay, so we're gonna save all of these values. Let me take off my camera. Okay, so here's what he did. So if we get back to the previous question. Okay, so we just answered the first question, number 1, right? So we calculated this mean value, expected duration of each activity. Okay. Okay, now the next question is draw the AOA network diagram. So previously I did it. So I'm gonna bring it up here. Okay, this is it. So I believe this time we do need only one dummy activity from 5 to 6. Okay. And what is the next question? Let me see. Okay, so the next question is for each node, we need to compute earliest time and latest time based on the expected durations. Okay, so what you need is, where's the values? Probably it's better to copy the value from Excel spreadsheet. So I'm gonna do this. So that's gonna be 3, 5, 6, 8, 6, 32, 22, 11, 16, and 20, and 5, right? So what you're going to do is using this expected value, That's the mean duration, right? For each activity, we need to compute the earliest time and the latest time. Oh. Okay. Sorry, I think I better use these two different screens. Okay, so let me just copy all of those values from this Excel spreadsheet. So for the activity A, the mean duration value is going to be 3. So I'm going to put it right here, 3. Okay. And for B, it's going to be 5, C, 6, D, 8, and E, 6, F, 32, G, 22, H, 11, I, 16, J, 20, and then K, 5. Okay. Okay. Now you should be able to compute the earliest time and the latest time for each activity, for each task, right? So as user, starting from time t equals 0, both activities A and C, the earliest start time can be 0, right? Yeah. And the earliest finish time is going to be 0 plus 3 equals 3, 0 plus 6 equals 6, right? So the earliest time for event number 1 is going to be 3. Earliest time for event number 2 is going to be 6, right? So we have 6 plus 8, which is 14. And here, 0 plus 5 becomes 5, right? And here, 3 plus 6 becomes 9. Now we need to compute the earliest time for event number 3. So that's going to be the largest value among these 3, right? Which is 14. So 14 plus 32, 46, right? So we have 46 here, and then 46 and 46, right? 46 plus 22 is 68. 46 plus 11, 57, right? So we have 57, and dummy activity has 0 duration, right? So we have 57 plus 0, 57. Now we need to determine earliest time for event number 6. That's going to be 68, right? There is a larger value between these two. And then we have 68 plus 16, 84, right? And down here we have 57 plus 20, 77, right? And the earliest time for event number 7 is going to be 84, right? So 84 plus 5, 89, right? So we know that the project can be completed as soon as 89 days, right? Okay, because we know that the project can be completed in 89 days. The latest time for the event number 8 is going to be 89, right? So we have 89 here, 89 minus 5, 84. And then we have 84, right? So 84 down here is 64, and then 68. So we have 68, 68, right? Minus 22, 46, minus 0, 68. So we have 68, 68. Am I doing correct? No, sorry. So when you determine the latest time for event number 5, we need to get the smallest value between this, right? So it's gonna be 64. So we have 64 down here instead of 68. 64 minus 11, 53, right? And again, the latest time for event number 4 is going to be smaller value between 46 and 53. So it's going to be 46. 46 minus 32, 14, right? Oh, it's 14, right? So we have 14, and then we have 14, 14, 14, right? 14 minus 8, 6, 14 minus 5, 9, 14 minus 6, 8, right? So we have 8 up here. 8 minus 3 is 5. And then we have 6. 6 minus 6, 0. Again, the smallest value among these three goes in there. So it's going to be 0. Okay. So it's pretty small size network diagram. So identifying the critical path using this method would be really easy and straightforward, right? So where do we have critical path? Critical path and critical activities. Critical path starting from 0. We have we go to number 2, and then event number 3, and then event number 4, right? And then event number 6, 7, 8, right? So 6, 7, and 8. That's our critical path. And the critical activities does include C, D, F, G, I, and K. And the project completion time is 89 days, right? So I believe the expected date of completion of this project is going to be August 29th. That's the 89 days from July the 1st, right? Okay. So we've completed question number 5. We answered for that. Now, the question number 6. Okay, so the chocolate cube has committed himself to a recording session beginning September the 8th. That's the 99 days from now on. And it's been asking you the probability that he will be able to begin recording in his own personal studio on that day. Okay, so now we need to find the mean and standard deviation of the sum of the durations on the critical path to answer for this question. So from the previous part, we already knew that the expected completion time of the project is 89 days, right? And so we need to compute the variance for the critical path first. So let's go back to the Excel spreadsheet. Okay, so we identified the critical activities as C. No, this is not C. Okay. Let me zoom out a little bit. Okay. So C is one of the critical activity, and D is another one, right? And then F, G, I, and then K. So I'm gonna mark it yellow, okay? So these are the critical activities. And we already know the summation of 1, 2, 3, 4, 5, 6. These values are 89, right? From here. We already identified that. That's going to be some of this, 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 this. Right? That's going to be 89. Sure. Now we need to get the same value. So we're gonna, I'm gonna just copy this, paste it. So from here, you know, expected value of CP is 89, right? Now the variance for the critical path gonna be this 48.6667, right? So the standard deviation, for the CP is going to be square root of this value, right? 48.6667. So how much is that? That's going to be SQRT, right? Square root of this value. So that's equal to 6.9762. Is that right? So what I can say is the completion time for these projects will follow the normal distribution. Okay, so let me write down the completion time for the project. As follows, normal distribution with the mean values of 89 days and the standard deviation of 6.9762. Is that right? So going back to our original question. The probability that the project will be completed within 99 days, right? So that's going to be less than equal to 99, right? And then we can standardize it. So as before, t minus 89 divided by 6.9762, right? Less than equal to 99 minus 89 divided by 6.9762. Then if we substitute this to x, x follows standard normal distribution with mean 0 and standard deviation of 1, right? So that's going to be identical to x less than equal to, how much is that? (99 minus 89 divided by 6.9762. Okay, that's going to be, let's say 1.433. So from Excel, like I said before, using the Excel function, that's going to be standard normal distribution. So norm dot s dot distribution, okay? And then we're going to put the g value, which is 1.433, right? And then put true. So we have this probability value equal to 92.4%. Okay, approximately. Does it make sense? Okay, now we are ready to answer for the last question, question number 7. Okay, so if his studio is not ready in 99 days, then the chocolate cube will be forced to lease his record company studio, which will cost $120K. And for $3,500 extra, Eagle Electric, the company hired for the electrical installation, will work double time. And each of the time estimates for this activity will therefore be reduced by 50%. Using an expected cost approach, determine if this extra 35K, I'm sorry, 3.5K should be spent. Okay, and how'd you answer for this? So according to this problem description, so if Eagle Electric is hired for how much? 3.5K, $3,000, $3,500, right? Then what's going to happen? So is that going to be activity G, right? Let me double check. Yeah, it's activity G. So installing electrical work, which is activity G. The duration for activity G will be reduced by 50%. So previously, how much was that? For activity G, previously, it's going to take 22 days, right? But by hiring Eagle Electric for $3,500, the time duration for activity G is going to be reduced to 11 days. Is that right? So what you need is, with these changes, you need to get the new critical path, okay? So where is G? Okay, so G is up here. Instead of 22, what do you need? Put the value of 11, okay? And then get the earliest time and latest time. And then determine the new critical path, the critical activities, okay? So from my previous computation, I've got the critical path, the new critical path is C, D, F, H, and JK. Okay. That's going to be C, D, F, this time H, J, K. That's the new critical path. Okay. And then the completion time in this case will be reduced to 82 days, okay, from 89 days, okay. So in this case, we need to do the similar computation as before. So this time, our new critical path gonna be C, D, F, and H, and JK. Okay. Oh, sorry. Do it again. It's going to be C, D, F, H, and JK. Right? This time I'm going to mark it with green. Okay. And of course, in this case, the mean value for the critical path is going to be 82, right? This is going to be this summation of this, 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 and this, right? It's going to be 82, right? Then I'm going to get the same formula. So the variance value for the new critical path would be 71.36111. So let me update these values. How do I change the color? Okay. This way. Just need to get this value. No. Okay. Okay. Now I change the color. So this value changes to 82, right? And the variance is 71.36111. Okay. Now we need to get the standard deviation. Okay, that's going to be square root of this value, right? That's going to be sorry, I'm not good at using the pen. So let me do this again. Okay, so instead of 6.9762, we have 8.44776. Okay, because we took the different value here, 71.36111, right? So what I can say is if you go down, oh, sorry, it doesn't move together. That's fine. We're gonna open up Word file. So what's gonna do is, okay, the new completion time for the project will follow normal distribution with mean value of 82 and then standard deviation value of 8.4476 from here, right? 82 and 8.4476, right? So again, we need to compute the probability that the project will be completed within 99 days. So as before, we need to standardize it. T minus 82 divided by 8.4476 less than equal to 99 minus 82 divided by 8.4476, right? So how much is that? Again, if you substitute X for this, then X will follow the standard normal distribution, right? And what is this value? 99 minus 82. Divided by 8.4476. How much is that? Okay, it's going to be 2.012. Okay. So as before, we need to get that value. That's going to be normal, standard normal distribution of 2.012 and then put true. So we've got the probability value of 0.97789. That's going to be 97.79%. Okay. Okay, so we need to compare these two probability values, right? So if I go back to the problem statement, okay. So what you need to do is to compute the expected cost of the project for both scenario, right? Without paying extra and with paying extra. Is that correct? Right? So let's do that then. So I'm not quite sure how to delete this. Okay, eraser. Okay. Okay. Good. So let's compute the expected cost of the project, right? And the first case, which is this, right, is without paying extra, which is $3,500, right? And down here, you're going to do the same thing for expected cost of project with paying extra $3,500, right? So with $3,500, so you need to add $3,500 plus 1 minus this probability, right? 0.9779, right? Times, I believe, $120,000. This, right? So you're gonna multiply by $120,000. Then how much you're gonna get this? Without paying extra, the expected cost of project is gonna be 1 minus this probability, right? 0.924 times the same value of 120,000. So you want to get these values, okay? So let's compute this. So first, 1 minus 0.924 times 120,000. How much is that? Okay, that's gonna be $9,120. How about with paying extra $3,500? That's gonna be 3,500 plus 1 minus 0.9779 times 120,000. How much is that? So we have down here $6,152. So what's the conclusion? What's your suggestion? This is way lower than this, right? So our conclusion is extra $3,500 should be spent, right? Because it's here gonna lower the total cost, right? So that's it. So that's how you can answer for the last question. So with this small example, I just showed you how the CPM and PERT can be implemented to the real world setting, okay? Okay, so I believe that's all for today. And so next time you are going to explore the new topic, which is the sensitivity analysis, I believe. Okay, thank you very much, everyone. I will see you next time then. Bye-bye.